Hello community, so great that you're back. Today we talk about the next big thing in AI LAM. So why this video? I looked at 124 AI research paper and I decided to go for this particular topic. You know why? I think it's the next big thing after deep research. And you know this deep research where we have the multi-turn tool usage capability of our largest reasoning models? Or think about Llama 3, this beautiful 27B open multilingual multimodal vision language model. Although it has no dedicated tool of function calling special tokens, you can do function calling if you are careful with your instruction code set. And I follow here the guide by Phil Schmidt. I can highly recommend this function calling guide for the Llama 3 27B. You have your complete Python notebook at Phil Schmidt's GitHub repo, explains everything here to you. You can use this here if you want on the net, or you go here if you want locally with Olama. But what's interesting is here the instruction following. So we tell our little AI, hey, listen, AI, at each turn, if you decide to invoke any of the functions, put it here in special tokens, you can now code in Python whatever you want, whatever you need for the reasoning part. And generated code should be readable, efficient, beautiful, and the response to a method will be wrapped here in special tokens. Use it to call more tools or general a helpful, friendly response. And then we say, little AI, when using a tool call, think step by step, our chain of thought, why and how it should be used. So we integrate now already with the latest models here, if you have a deep reasoning, how to use external tools and to what extent to use external tools to support here the deep thinking. But you might say, hey, but wait, this is code, no? It means it has a structure pattern, and guess what? I know a machine, any code LLM, that is specialized in structured pattern, in the detection and in the generation of structural pattern. So why not integrate this into your next AI? So, kind of another perspective, we have our beautiful reasoning models, the O3, the O1, the R1, the L1, the S1, whatever you call it, where we have advanced test time scaling. You go in the simplest case for a linear chain of thought, or a little bit more advanced to non-linear graph structures in your reasoning patterns. And now you just say, listen, if it has access to a code LLM, and it needs here some verification. So it's, okay, solve this argument or this decision you have to take here with a Python validation. Code a virtual experiment in Python, C++, whatever you like, and return the result for the further reasoning, for further deciding here what to do in the reasoning if you want sequence. So you feed it back and you have here, if you want to calculate, I don't know, the volume of some particular body or whatever, you have numerical results that will help you in your reasoning process, or some new financial data calculated here at the current time. Now you know that this is just all what we call tool use. Doesn't matter if a particular tool has some particular functionalities, it is tool use. So let's open up this video and let's see how we can code a generalization of this. And in our today's paper, they are talking here about agent models. I'm not happy about the term, but never mind. So what we have now a chain of actions and a generation of this chain of actions, when and how to use external tools. And now the AI is deciding on this. So what we have is, looking here at the terminology, in every agent we have an intelligent core. If it's not rule-based agent, if we have an AI agent, we have an LLM or a VLM or whatever. So saying now an agent model where we have the model as the core inherently in the definition of the agent, okay, we just go with this publication, never mind agent models. I like to call it large actions or agent models. More about this later on. But what is the core? The core is we have our chain of thought of reasoning, and now we have to bring in the chain of action, the interactions with the environment. If we decide, hey, now I need to write a code experiment, now I need to write a C++ program to run this numerical simulation on a supercomputer for a physical experiment, for a chemical experiment, for a material science experiment, or for some financial optimization. And you know an agent, you say, hey, this is what we know, no? Task planning is a capability of an agent. No? Tool usage. Already a year ago, this was what agents are doing. So now we bring it together. We have our large reasoning models, the O3, for example, or the DeepSeek R1. You know, they internalize the capability of task planning. They generate chain of thoughts in the linear case. And now we further enhance those systems here with a chain of action. So they decide how to interact with the environment, what tools to write, to activate, to connect to utilize, get a result, and continue with your reasoning without any human interaction. So this kind, authors argue, goes from a reasoning model, now switches over to an agent model. If you think about what is the difference to our current agentic workflow, now you know if we do this, I don't know, whatever you like on the agent system, it relies here on prompt-based methods to simulate here the interplay between a linear thought structure and an action structure. And now the new idea is, hey, we have AI. Why should we write templates? Why should we write, I don't know, self-chain structures if we can have AI structures that does this? So we tell now our AI, hi, you now have the task to learn chain of thought and the chain of action patterns that are coupled together. I give you some examples in the training dataset, but you as AI, you find now the best configuration. It is an optimization problem. And we will use this for the next generation of autonomous deep research. You know those agents that OpenAI said maybe $20,000 per month? This is what we're talking about. So we need a spark of genius, you know this. So in the easiest case, just to show you an image, no? What we had our old chatbot idea where the humans were talking here, or on your phone you were typing or speaking to your, I don't know, O3 model. And then we had these reasoning models like O3, and you had to wait for 1 minute, 2 minutes, 15 minutes, because what's happening was here, this slow thinking, this mode 2 thinking, we had a test time compute scaling or inference compute scaling, and the model took time with your specific prompt to think about this, to think about a solution. And now in the latest step, what we have a look today, we say, great, and now the model can generate tools, can generate code to run virtual environments, to run virtual decision models, to run virtual mathematical financial calculation models, interact with the environment, and come back. Because if we're already waiting here 2 to 5 minutes, okay, so now we are waiting 3 to 7 minutes. You see? And we have in today's paper a definition which is beautiful, so I have to show this to you. So they define here this term agent model, okay? A generative model built upon a reasoning model, enhanced through end-to-end task-oriented tool-augmented training. So this means produce a sequence of interleaved reasoning, or a chain of thought, and a chain of action steps, where each action invokes here a tool to interact with the external environment. Real nice, absolute beautiful idea. Now, you know, if you have seen my last video on a little bit of mathematic AI, that the inference here of this particular agent model is easily in our standard understanding here. It's a partially observable Markov decision process. And the state is now defined simply with the parameters here, the initial environment state, the task context, and a sequence generated here from 1 to n, so far combining all the tokens emitted by the model and responses from the environment. Yes, because we are talking about an agent, and an agent per definition interacts with its environment. Focusing now on the tokens, you will see that our exercise today becomes really simple, because we will stick to our mathematical scheme. For the autoregressive calculation, we just add a number of complexities. So think about what are actions here in an autoregressive system. actions here in this partial observable Markov decision process are just the generation of the next token. You know this from my last video, and you know that pi theta is just the policy model, the policy parameterized by all the functions theta. So think about it. At each step, we have now a specific policy, and this policy model can generate now one of the following types of tokens. Now, you know the first one, no? The thinking token, our chain of thought that we have already. And of course, we have a reasoning sequence generated where each or sub I is a token in the reasoning process. But you know what? You know what we can do? We can have another type of token. Let's go with an action token. Because for a neural network, it doesn't really depend what kind it is if you just tell it what to do with it. So, if we have an action token, invokes a tool to interact with the environment contributing to the chain of action. So this token signals here the transition from a thought to an action, deciding now when to action, and this is learned, of course, with training data. So following this token, the model internally generates now or acquires from the environment the action type, for example, search the internet, the action parameters, a detailed search query, and a response by the action invocation. So whatever you get back, and you know this from the old React model. Yeah? The environment response here is O. And with this, we can now generate the final token, the answer. And the answer token, the special token, is simply the output of the final response, indicating here the task completion or termination due to exceeding here predefined budget. So the core idea is clear, no? We just work with our tokens. And again, we don't continue here with our classical agentic workflow and agentic system where you rely here on external prompt optimization, or you rely here on sort scripts or sort templates or whatever you have to manage those interactions. When you define when and how to use those tools here. But we want now that the AI, the agent model now internalizes here and kind of deduct a logic of tool use as part of its learned behavior. So no scripts anymore, no predefined prompt structures. Let the system learn autonomous. Short interrupt because I'm a little bit confused here. You know, all the authors, they stick not really to a common notation. So what we have? LLM is a large language model. A VLM is a vision language model. A VLA is a vision language action model. An FM is a foundation model. An RM was originally the reasoning model. You know, this test time compute scaling, this inference compute, when we wait 2 to 5 minutes. And this was originally only the O1, the O3, and the R1. But then, because when we did the distillation of an R1, we went to smaller reasoning model. And then the reasoning model switched to, because they are huge in their size, to the large reasoning models. So what was the RM now are the large reasoning models. And now this action here, we have LAM. And you might think it's the large action model. But this we already have here now, the vision language action model. So the authors decided to call this now the large agent model. So yeah, it's a little bit confusing. So I just want to keep here the notation in each video with each publication, either here from our friends in the US or our friends in China or our friends somewhere else in the world. They all use here kind of their own notation. And I think I just have to show this to you so you understand. If I talk about a certain system and I use an abbreviation, that you know exactly what I'm talking about. So just to be clear, the large reasoning model was with a chain of thought, a linear chain of thought, and later it developed here to a graph structure, a graph of thought. And now today in this video, we're talking about here a large reasoning model with this chain of thought capability. And now we complement it is with interface to the environment, so with a chain of action. And now this new model is now called here, by definition, by the authors of this paper, a large agent model. And since has this problem for me to understand why this should be an agent, I found a memnotechnical bridge for me, because you remember, an action is always an interaction with an environment, and an environment defines per definition an agent. So now I remember that this is a large agent model. Beautiful. So our large agent model. Here you have the pseudocode. You generate the chain of thought. You generate here the chain of action. You generate your action type. You map it. You invoke the tools. You acquire the response. You generate your answer. Easy. But what's interesting is, how do we train those systems? We understand how it works here, but how we do the training for this agent model. And you're not going to believe it. We have a new marketing term, autocore, so an automatic chain of action. Beautiful. What's important for us? 2 stages, supervised fine-tuning and reinforcement learning. Beautiful. So let's have a look in detail at these 2 stages, because it turns out there is something beautiful happening in those systems. The policy model that we're going to use now for our LAM will develop here an internal world model. This is something we know from robotics now, that if you want the robot interacting with its environment, has kind of simulated here the reality into a simplified world model, an internal world model, and this is exactly what we are going to build now. Now, this world model has a particular task. This model has to understand its environment and possible responses by the environment, for which it has to train how to respond to this. So this is, if you want, this is here a virtual simulation of the external world, and how the system learns in this virtual sandbox to train itself how to respond, and therefore it has to have a good virtual, if you want, sandboxed model of the real world model. Let's do this. The first one is, of course, a supervised fine-tuning stage, the classical one. Now, interesting, here we go with 3 different supervised fine-tuning stages, and each stage has a particular data set and a particular task, so that the system learns something special. Let's start here with the first, and here we teach simply the model to autonomously decide when to do an action, when to initiate here an action, and maybe an external tool use. I will tell you more about these training data sets in a second. The second one is, this teaches the model how to action itself, including here determine the action type and the specific parameter of this action. And then here we build now finally the training the model to predict the environment response alongside the action. So we have a joint optimization of the action generation and the observation prediction by our model, and therefore it equips here the policy model with an implicit world model. So this will be a lot of training data given about the complexity that we want to solve with this LAM. And then we build upon this, no? The reinforcement learning, the alignment that we're gonna have is 2 stages. The first one is about the simulated environment, the internal world model, and the second is then the real, verified and planned in the virtual sandbox, the real interaction with the environment. So we will use here a particular data set, more about this in a second. So after rolling out here the action, the policy model itself continues to generate here the observation, leveraging here the learned internal world model from our supervised fine-tuning. So this allows here for extensive sampling to explore diverse action sequences, try it out, run experiment, but you are in the, if you want, real cheap here virtual space where nothing can happen. And then, after we trained this, we learned it, we go to the real environment, because now the model has to interact with the real environment to receive observation and validate its theoretical reasoning. You might say, great, beautiful. So here we have the study. This is from March 9, 2025, and this is from Beijing Jiangming University. A beautiful study, some grand new ideas. Just the name, the agent model. Okay, let's go with LAMs. So, internalization of the generation of a chain of action, enabling the model to autonomously decide and reason when and how to use external tools. No templates, no nothing anymore. And when we start, first point, data generation. So they decided here, the authors, we used here the DeepSeek R1 Distill Q132B model. This is from my last video. You know exactly what is here this distillation process for the data generation. So we work with synthetic data. And of course, for the tool invocation, they have a wiki search engine. Makes sense. Now the integration of this tool enables you the model to simulate the process of obtaining additional information through external resources during the data generation, thereby training the model to intelligently trigger external tool calls when facing now the real complex reasoning task, further enhancing its performance. The first set of data, chain of thought data. You know this is classical, no? 10,000 samples, they use here the DeepSeek R1 Distill Q132B model here with a chain of thought prompt designed to elicit step-by-step reasoning. So we generate here a pure chain of thought process without, careful in the first step, any external tool use. So we have a sequential reasoning. Then we come to the synthetic chain of action data. Another 10,000 samples here. We use here a particular chain of action prompt that instructs here our model to invoke here a search tool when encountering knowledge gaps. Therefore, we enable the tool-assisted reasoning phase. So the model now triggers here the action token, the special token, to call now a search tool. It retrieves here the necessary information, let's say from Google, and it resumes reasoning based on the results that it retrieved from Google or any other search engine. So this means now the generated chain of thought data captures now the full chain, the question, the query that a human has, the reasoning process here itself. But careful, the reasoning process now includes the action trigger, the observation from the environment, and the subsequent reasoning, and if you have, the final answer. So this data structure enables now the model to learn when and how to trigger actions. So this is a particular important synthetic data set, and here I think you can improve the performance if you are really carefully selecting the best results only. Now, for the third dataset, the training dataset, we need a COT plus 8 dataset. And you know this, contrastive pairs. So we generate now synthetic contrastive pairs by altering here the reasoning trajectory at a specific point. Either inserting an action trigger to enable the tool use or removing it to enforce internal reasoning. So each pair diverges on whether tool usage is permitted thereafter, leading now to a scenario where either chain of thought is incorrect, but the chain of action is correct, or vice versa. And this familiar training system, we train these contrastive pairs here with what we know, the contrastive loss function. We know this from years ago from the BERT system, to help the model learn when to trigger this action, to create a tool, produce some code, run the code, validate here, get an answer and come back to the decision process, or when to rely purely on its internal reasoning. So here this training data set is really important to have a high quality data set. Otherwise, you can find out that the system later in inference run will not produce the best results. So now we have the data. Now, let's look at the training process itself. Remember, we have supervised fine-tuning stage 1 and stage 2 and stage 3. So for the training now, the authors tell us, so we select here 1500 COT plus A contrastive data points. And this is the training set for our supervised fine-tune stage 1. Then for the stage 2 and 3, we combine 5000 chain of action data points with 1000 chain of thought data points to instill the capability of how to execute an action. And you might say, hey, why do we need an additional 1000 chain of thought? And they explain this because it is including this chain of thought samples ensure that a model retains its ability to solve tasks without external tools. So preventing here an over-reliance on action and balancing here the reasoning with the tool usage. So you see, there is still here this problem that some catastrophic forgetting might happen after 3 stages of supervised fine-tuning. Therefore, at the end, they go again with 1000 chain of thought samples. Interesting to see that we still have kind of those old weaknesses, we still carry them with us. Building now in this supervised fine-tuning stage, now we come to the reinforcement learning, and you know there's only one if you want to do a modern system, GRPO, Group Relative Policy Optimization, matching the rule reward system, beautiful. Again, we have a 2-stage system for reinforcement learning. The first one is for the simulated environment, for this inner world model, and then the interactions for the real environment where we validate what we learned in the sandbox of our simulated environment. Here, this internal world model that was generated during the supervised fine-tuning phase is so important because you can freely explore here a diverse range of action strategy in our sandbox, and this is just gorgeous. Then we move out in the real world, actual tools, actual tool calls to obtain here the real world feedback, and then we will adapt our theoretical strategies now in the real strategies here for the system. Great. So you see, the idea is beautiful. We just go another step beyond chain of thought to chain of action, and we merge them together. We have a beautiful fusion. We know now that we need a lot of training data. We know that we go with a classical supervised fine-tuning step and with a reinforcement learning step. And now let's look at the performance. What model did they use for their experiment? Well, of course, a small one. It has to be a 7B model because there was a lot of supervised fine-tuning to do and a lot of reinforcement learning. But they go not, as I showed you in my last video, for the quantized, but they go for a distilled version. So they go for the official DeepSeek R1 Distill Q1 7B model for the auto-core training. Remember the marketing term auto-core? Yes, I know. Now, interestingly, if you have a look at their GitHub, and this is open source, you can have access to all the data I'll show you in a second. They used a specific engine here for reinforcement learning. And I was not aware of this volcano engine reinforcement learning for LLMs. It was based here on the paper here from University of Hong Kong and ByteDance and University of Hong Kong. Real interesting paper here from Hybrid Flow, and this here is if you want the open source version of Hybrid Flow, this Volcano engine reinforcement learning of LLM. So this is what they used, but here I have now the complete GitHub repo. Here you have everything available. MIT license, isn't this beautiful? And hardly anybody noticed that we have this. So I thought, hey, wow. I have to show you, this is an amazing system. It is open source. It is available for you. Try it out. Now, there is a lot to talk about the performance benchmark and new ideas. I give you everything here in one view. So at first here, the top we have here the classical R1 Distill Q17B. If you go for the vanilla version, and then we have the super duper DeepSeek R1. You're not going to believe it, in all the tests and all the benchmark that we have here, the R1, the big one, not the quantized, not the distilled, the real R1 has the best results. What a surprise. And then, we go with the classical React, this old-fashioned React system. And then we go for, in color I have here, only the supervised fine-tuning and then the reinforcement learning that builds upon the supervised fine-tuning in different stages. And what I love is that they give you here the performance data for stage 1, for stage 2, for stage 1 and 2, and for stage 1 and 2 and 3. And you see there's a lot of things going on. So whatever benchmark you choose, never mind, I go here for the average of the LLM, yeah? Please, if you like something else, go for a detailed structure. Now, what we see here, of course, it will never, a 7B will not reach here the official DeepSeek R1 unquantized and undistilled because, this is no match. but we see where we are. Now, let's have a look here at the next one. Let's say we go here with the reinforcement learning stage 1, and we have the supervised fine-tuning stage 1, 2, and 3. Let's look at the result. This is 37.2. This is not really better than supervised fine-tuning stage 1, 2, 3 that had 37.7. So why the performance is declining, going back, if we add a reinforcement learning? How is this possible? I mean, the reinforcement learning should help further align the system, increase the performance. Not in phase 1. But if you do stage 1 and 2 from reinforcement learning, it goes again a little bit up. So from 37.7, now with reinforcement learning complete, we have 38.9. Interesting. So you see, the incremental improvements are rather marginal, and this tells me, hey, we do have here a lot of opportunities to further increase the performance, and I have so many new beautiful ideas just looking at this, and maybe you too, you will decide, hey, I will focus now on particular stages, but whatever it is, never mind. And therefore, if you combine all the different combinations, for example, you see here the last one, the supervised fine-tuning stage 1 and 2 only without 3, and only reinforcement stage 2 without stage 1 gives you a result 38.5. That is really outstanding here in this interval of the performance data. So, do we need here the third one? Because look, if we have a supervised fine-tuning 1, 2, 3, the performance data indicate we reduce our performance, because if we only have stage 1 and 2, we are 38%, and if we add 3, we fall down to 37%. So there's something inherently going on, but hey, this is my first view, so we have to have some experiments. Everything is open source, this is great, have a look yourself, so we can have new ideas, new optimization methodologies. But you know what? There's also some other things I would like to talk about. Why should we humans use here our code editors, our courses, or whatever you have? Please go with whatever you have, or if you see this to a later time, you will have the latest thing here. Why should we code? We have AI for patterns, and code is nothing like a structured pattern. Think about this. We have a complex problem in finance, in medical, in pharmaceutical, in wherever you are, in physics. So what we do is classical, no? We have a decomposition in simpler, lower complexity sub-problems, and we find solution steps for those sub-problems. So we decompose here the complexity into lower complexities, and then we have now a set of tools. And you see what's happening now. If we train an AI on the complete system to autonomously decide how to do the complexity reduction simplification, how to choose which available tool already here in the training of the new agent, you don't need to code anymore, you know? Because if a solution step would be build a website, regularly tweet on my particular topic, optimize here the pre-sale of my products or of my services, run here a specific hype campaign to hype my product, or build here a brand of my company, you don't have to do this as a human anymore, because whatever you use, Python, C++, SQL, internet, finance, social platforms, these are just tools for an AI system. So the AI will decide, you give it a complex problems, hey, I want to build here, I don't know, a company with a product idea, do it, build a website, tweet here on the social platforms, start a pre-sale, go whatever you find successful as a hype, run some A/B tests, run some experiments in the internet on the social platforms, refine here maybe even the products itself, and build my brand. Those are just tools. You don't need anything anymore from the human side, but come up with an AI that is able to do this. So remember, we go beyond templates, we go beyond any structured information for this. So we kind of have an evolution from an individual competence here to a collective artificial intelligence with a multi-agent AI system that is able to perform exactly those intertwined chain of thoughts and chain of action and run experiment here in a sandbox or in real environment for your specific task. And now you might say, hey, wait a minute, I have an idea. Maybe OpenAI $20,000 next-gen agent, isn't this somewhere close to what you just talked about in this video? It is just a wild idea. But I think, just looking at AI research, what we are able to do now, I think this will be the next step in AI. And I know that a lot of people say, hey, I'm coder, this is my job, this is my business. But code is pattern, and intelligent code detection and intelligent code generation is the business of AI. I don't think we will stop there and say, up until this step and not further. The development will go on, and therefore this system will become an interactive autonomous system. And I can imagine if OpenAI has invested in this already for more than a year, I mean, we are not the first to have this sort for a complete system, and I think then the price tag of $20,000 would kind of be justified. I mean, depending here on the performance of this system. But now I think, I personally think I have an idea, maybe just a glimpse of an idea, what will be the next step in AI. And it will be not so much about this, what is it called, super intelligent, hyper intelligence, super duper intelligence. It will be about integration. You as a human would just define a complex problem, and the system learned here from the complete internet, from every startup, from every internet page, from every book ever written here on marketing, from every book ever written how to do the perfect pre-sale, on every online Reddit, how to build your brand. All of this is available. Do it. You have the tools. You have access to the platforms. The AI can perform it. And therefore, I think this price tag of $20,000 somehow seems reasonable. If you do agree with me, great. If you do not agree with me, even better. So why not leave a comment here for this video? And if you're interested and you subscribe, I see you in my next one.